Okay, so let us begin the final talk of the day. We have the final talk by Cyril from Center of Computational Astrophysics, Flatiron Institute, USA, and he's going to talk about cosmic magnetic shear of blazars.
Thank you so much. Yes, so today I'd like to tell you a story about how we are planning to search, or how we are currently searching for intergalactic magnetic fields using an astrophysical probe, namely Blazars in the GV sky. To give a quick overview of what I will say, I'll first tell you what the current status is of intergalactic magnetic fields and their relationship to a phenomena called blazar halos that we have not yet observed. That's quite interesting. Then I will tell you how we actually go to search for a signal of these fields in the blazars. It'll be using a standard technique known in cosmology that is routinely utilized for decades. And then I'll tell you some bits about how this story is somewhat imperfect and how there are actually some sources of noise in our measurement of interest. And finally, I'll tell you how other methods that employ blazars relate to the method that I'm speaking of today. To give you sort of a result right off the bat, the takeaway that you should remember at this stage is that Fermi is sensitive to intergalactic magnetic fields with strength roughly about 10 to the minus 16 to 10 to the minus 14 Gauss and coherence lengths of 1 to 100 megaparsecs. So these are extremely weak fields with very long coherence lengths. Large scale, weak intergalactic magnetic fields. With that, let me give you a bit of motivation for why and we should think about these questions and what they actually are. Intergalactic magnetic fields are a great quantity, for they already say what they are. They are magnetic fields that live between galaxies. These are not to be confused with galactic magnetic fields. And these are also typically, what I have in mind, are not magnetic fields that are attached to some large-scale structure of the universe, namely filaments. Filaments comprise about 30% of the universe's volume or so, and they host magnetic fields in them. However, an intergalactic magnetic field more precisely refers to magnetic fields that exist, that's a volume filling. So it namely exists in voids as well. And we have not observed such magnetic fields to date. So this is a search, and in order to see what they are, here's a sort of cartoon on the left that I'm picturing, and the intensity of the color from red to blue shows sort of the strength of the magnetic field, encapsulated by the parameter B naught. So the magnetic field is not some constant thing in the universe. It has inhomogeneities, and it is described by a stochastic random variable. So it is a stochastic field. And these inhomogeneities have this root mean square amplitude, B naught, but they also come with some coherence length. So they tend to stay constant on patches of size roughly lambda b or so. And you can see even in this picture that there are patches or so that have some constant coloring. And finally, even though there's some coherence length that shows the typical size of these patches, they actually come in a distribution. And if these distributions follow a power law, that power law index is given by NB. Now, given this picture, intergalactic magnetic fields can be motivated probably most saliently through galactic magnetic fields, in fact. So while IGMFs have not been observed, GFs have been. It's well known that all galaxies host a magnetic field, and they tend to have magnetic fields of, let's say, at the weakest end of the spectrum, microgauss or so. And while we know of their presence, we do not know how they arise. The current leading hypothesis is that given a seed magnetic field, there's an astrophysical process by the name of the alpha dynamo mechanism that can then amplify that seed magnetic field into the sort of microgauss magnetic fields that we observe in galaxies today. The intergalactic magnetic field of interest here, that is volume filling, that is in cosmological in origin, would provide a seed precisely for this mechanism to take place. There are other astrophysical methods that have been proposed that could also do this, that do not rely on cosmological ones. However, I will not be discussing them in this talk today. Moreover, some intergalactic magnetic fields can actually arise in models of baryogenesis, namely ones that involve an axion or some CP-odd coupling to electromagnetism. So in these cases, you have a tachyonic instability in your theory for photons, and that leads to a parity-odd magnetic field. And parity-odd magnetic fields are quite rare to come by. They don't often happen in many other theories. I mean, generically in axionic theories they can, but it is a nice sort of probe potentially of baryogenesis as a result. Moreover, magnetic fields can arise even in models of inflation. Your first naive guess that magnetic fields cannot exist in inflation due to its exponential expansion is a good one, because typically conformal couplings to photons tells you that the photon strength should decay with the scale factor as it exponentially expands. However, if you just introduce some, couplings that break conformality in your U1 field, namely, let's say if you throw out a conformal coupling through a coupling that looks like gravitationally induced mass, it looks like Ricci scale or R times a mu, or something to that nature, you can therefore produce magnetic fields even in the epoch of inflation. And so it would be nice. Intergalactic magnetic fields can give a probe, therefore, of inflation. And finally, various different phase transitions, whether they be modifications of the standard electroweak phase transition or otherwise, can give rise to magnetic fields. So, given that, let's move on to this quick sort of review of sorts. So, as I said, intergalactic magnetic fields are specified by 3 parameters in general. However, typically people show only 2 in this plot for the dependence on the index. It tends to be suppressed. It's a convention. And here I'm showing sort of what is the most kind of common constraint plots that you would see if you're in, let's say, cosmological analyses. For people often speak of nano-Gauss magnetic fields. Now, on the far left, you can see that and also I should point out that as you can tell by the x-axis, there is a wide range of coherence lengths shown on the x-axis. You go from 10 to the minus 13 megaparsecs all the way up to 10 to the 3. And so at the very end of the left, you have that very small scale, a small coherence length scale, magnetic fields cannot exist because they will magnetically diffuse in magnetohydrodynamics. So they just cannot live, they diffuse away, and you can effectively say you don't rule them out necessarily, but they just do not exist. Now, at the very top, you have a Zeeman splitting. So, as I said, we have micro-Gauss magnetic fields. If magnetic fields had stronger than or so micro-Gauss strength, then they would induce splittings in atomic lines that would be larger than those that we observed. And so you can immediately sort of rule that out. Presence of magnetic fields will also induce some Faraday rotation on radio emission far, and we do not observe that, as well as there would be some induced distortions onto the CMB and temperatures. There's also dissipation if the magnetic fields exist in the early times that would lead to some also sort of spectral distortions that's indicated by the early magnetic dissipation. JS19 is another analysis of CMB anisotropies that does a more sophisticated numerical simulation with MHD and whatnot, and it's shown there in the purple. On the far right isn't also a constraint. It's just indicating where the horizon is. You can, in principle, have a constant magnetic field with larger than horizon size. It's just that the phenomenology all sort of collapses into one point. It makes no difference where you really are. Okay. Now, while those are sort of the common constraints that we see, Blazars are, in fact, I would argue, the most precise probes of magnetic fields. But first, let's understand how they relate to one another. So let's draw a picture first without any magnetic field and a blazar. So as a quick reminder, a blazar, you can just think of it as a supermassive black hole surrounded by an optically thick, geometrically thin accretion disk. And then it has, most importantly, an ionized jet of plasma perpendicular to this accretion disk. And that jet is pointed towards us. Now, with that in mind, if you have a blazar indicated by the star that is pointed towards us, it will emit TeV photons. These photons will travel distances of approximately, let's say, 800 megaparsecs or so, really hundreds, cosmological distances you should be thinking, away from the blazar, indicated by purple, before it scatters off of extragalactic background light. In particular, it goes off of optical and infrared light. And once it does that, it pair produces, and pair produces electrons and positrons. And these pairs of charged leptons then traverse a comparatively short distance, less than a megaparsec or so, before they scatter off of the CMB. Once they scatter off of the CMB, and they do so, thousands of times, they will deposit energy and into the photons and upscatter them to GeV energies, and these photons will then travel to us today. Because all of these processes are coming from a TeV initial photon, all the subsequent trajectories of this electromagnetic cascade will follow in a straight line. They're highly boosted, large Lorentz factors. Now, when you have an intergalactic magnetic field, the straight line emission trajectory can be altered, in fact, and you can get deflected trajectories. And that's because upon pair production, if you have an intergalactic magnetic field, and let's say that it's going out of the page, it will send electrons towards us and positrons away from us. If I looked at the deflected trajectory on the other side, you'd get the opposite effect. But in the end, they would still upscatter the photons to GeV energies. And so, given this picture, you can immediately see how this is very similar to, say, something like gravitational lensing in just cosmological surveys that people routinely use for analysis of just the contents of the universe. But here we want to rather investigate the nature of the intergalactic magnetic field. So, what I have said so far is how people typically utilize blazars to constrain them. And so here's a constraint plot of utilizing blazars. Now, there's two immediate things I will say about this plot. One is that this plot immediately seems like all magnetic fields are ruled out. This is a thing that is somewhat surprising and maybe not always appreciated by the community. But it is sort of the current status of intergalactic magnetic fields if one takes at face value all constraints today. One of my takeaways that I would like to sort of peddle is that we need to be more careful when making these constraint plots. And I'll tell you why that is in a moment. And the second thing I would like to say is something not about necessarily physics as much as just coloring, because this plot can sometimes be very difficult to read. So let me describe as follows. So the way you should be reading this plot is that there are three contours that are green, and these green contours continue onwards behind the purple ones. So you first should see one at the bottom that is dark green. It continues on to the left and upwards. Then there's a lighter green. It does the same. And then there's even a lighter green at the third one that goes and moves off to the left. These constraints also continue onwards, leftwards, that down to the 10 to the minus 13 scale that we had shown in the previous plot before. There is also an additional purple contour that looks like it comes off and is parallel to the green contour, the lightest most green contour, and it therefore has its own scaling when it starts to go below about 10 to the minus 1 megaparsecs. You should ignore the orange contours and the red box, primarily because those were tentative detections at the time of making this plot that have since been ruled out. And then also you should see this black sort of hashed region is also being ruled out. Now, given that we have colors, and I've said that it looks like everything is ruled out, let me tell you why we shouldn't necessarily trust this plot. And that is precisely because even though, and also I should make the statement that my goal in mind is to say that the method that I will talk about today is going to actually look in this blue region here that I'm going to argue is still something that is not ruled out despite it seemingly being so in this. And the reason why is because actually the story that I told you at the beginning is while a standard model phenomena that we have known from the 60s has not been observed yet. That is, those TeV photons that lead to secondary GeV photons we have not seen. Blazar halos, we have not seen to date. This is sort of confusing, as once again, this is a standard model process that is fairly straightforward to calculate and has been, scrutinized over, over half a century at this point. And so as a result, you then have to come into the question of whether everything I told you about the story is actually true. And it turns out that every explanation that you can sort of think of isn't really good. So first of all, if I remind the beginning of the story, I said blazars emit TV photons. The first explanation for why we don't observe these secondary GV photons maybe just be that blazars have some spectral cutoff. So if there's some cutoff in the emission spectrum of blazars, then maybe they don't emit TV. However, this is in strong tension with observations of local blazars at these high energy spectra. So Cherenkov telescope arrays actually can observe emission at the TV energies. And so if you want to hypothesize that the more distant blazars observed from Fermi don't emit in the TV, then you would have to invoke some sort of like strange fine-tuning of your model where distant blazars do not emit in the TV and nearby ones do. This is in people have looked at a variety of ways you can finagle this sort of astrophysical phenomena, and it just seems to not work. Second of all, you can invoke the intergalactic magnetic field, and this is sort of like the most common explanation. If you have an intergalactic magnetic field, then the emission along the line of sight will be deflected off the line of sight, and so you wouldn't see these photons necessarily when looking straight at a blazar. As a quick note, Fermi, when they look at blazars, they appear as point sources. So really all the emission should be coming from like one pixel in your data at the end of the day. So third, you may even start to say, well, we have a standard model. We definitely have evidence for physics beyond the standard model. Why can't it just be some BSM phenomena that is causing this? And actually, people have looked at a variety of models that can hopefully yield some hint to what's going on. However, all of these are sort of poor explanations. So your maybe first guess is an axion, because axions can, in the presence of a magnetic field, can convert the initial primary TeV photons into axions, which would then prevent the production of an electromagnetic cascade afterwards. However, the reason of parameter space that would actually yield a solution to this tension is ruled out by white dwarf polarization measurements. That is, if you had the correct axion to solve this problem, you would also induce too large of a linear polarization in white dwarfs that we do not observe. You could also say you have a dark photon. However, the dark photon just does not produce really that much conversion mechanism between the photon and the dark photon in order to alleviate this tension. For you need extremely light photons in the first place, and also the resonant condition that is required is just not sufficient enough to make enough mixing. Finally, and most controversially, you can invoke plasma instabilities. Plasma physics is a field wrought with instabilities, and in particular, the instability of interest here is something called an oblique instability. This instability would drain energy away from the charged electrons as they are pair produced, and release it maybe as, let's say, heat to the IgM. And so then these electrons would not be able to upscatter the C and B to the GeV photons in the first place. I should note that this mechanism is often debated in the literature over maybe a decade or so at this point, and every paper you will read on this will indicate that it is very controversial, but maybe necessary if we actually rule out intergalactic magnetic fields. So given that these are sort of like the four possible explanations you could even imagine, going as far as outside of our standard model to, exotic plasma physics, and none of them seem to be doing the work, it sort of invites us to revisit sort of these constraints and whether we've been too quick to rule out any one of these explanations. And so that is why I'm here arguing that this blue box that I've written is sort of the prime location, because it is above the most conservative bound given by Fermi, which is indicated in purple, and it's sort of below this sort of hashed black constraint. So now let me talk a little bit about what the colors mean. So the purple constraints, as I just mentioned, are constraints from the Fermi collaboration. They come from a combination of stacking blazars as well as folding in information from Cherenkov telescope arrays about the spectrum. They do not see a bump in the spectrum, and so you need to somehow fit that with the presence of a magnetic field. Now, at the most top, it is the most optimistic curve, and the difference between the most optimistic and conservative purple contour constraints are primarily given by the activity of a blazar. If blazars have been, active all the time for the ages of the universe or even shorter, then you would expect to see this emission for sure. But if the blazars of interest have only been active only most recently, then you don't expect to see expect very bright signals because there just aren't as many photons to be observed. And so that leads to the delineation. And I would, as a very conservative person, take the most bottom one as probably like a fair assessment. But if you're slightly more optimistic, you can bump this curve a little bit above it, but not too far. The green curves are a variety of different other blazar-based constraints that also fold in time delay explanation. So because you're undergoing deflected trajectories, you will also see some delay in the appearance of the photon. And if you can see, the exact same spectrum appearing some like characteristic time delay away, you can say that is because of a deflected trajectory, and namely a presence of a magnetic field. The hashed region is so also I should say, but all of these green and purple constraints are lower limits. These are very different than your upper limit constraints that you typically think of. They effectively are an indirect evidence of a presence of a magnetic field. Sort of a weird thing to think about, and some people frame it that way. I wouldn't necessarily frame it in that precise way, but it is a lower limit. Because if you had no magnetic field, you just wouldn't be able to fit the spectra that we observed. Now, the hashed region is actually ruled out again by sort of blazars in the GeV sky, but for a very different reason. So if you go above a characteristic strength of about 10 to the minus 15 or 10 to the minus 14 Gauss, the story I told you about deflected trajectory slightly changes because and rather than going some weak deflection that deflects you, just perturbs the direction you're going in slightly, in fact, the magnetic field will cause your charged leptons to undergo actual full circular rotation. So if you go full circular rotation, then when you go upon, that finishing that rotation and upscattering the CMB, the direction of that CMB photon is kind of just random. And so you therefore contribute not to some like small region around the blazar, but just isotropically to the GeV emission that we see. And we actually can delineate the contributions to the observed isotropic gamma ray background quite well. And if you say that, well, we know the existence of star-forming galaxies, misaligned AGN, radio galaxies, whatever, and you budget out what they have, and you then try and fold in this extra emission from blazars that could then get isotropically emitted in this electromagnetic cascade, you just overshoot the budget way too much. And so you just know you don't have very strong magnetic fields, given the blazars. So that's why this blue box doesn't extend past that black hashed line and sort of sits in between the most conservative Fermi and this sort of upper line isotropic constraint. All right. So now let's talk about what we're doing right now to actually search for them and how this method is a bit more robust. So as a reminder, here's the picture of interest. You have some blazar that's located along the line of sight, a co-moving distance key sub s, so that's source. And then, there's this deflected trajectory that undergoes pair production, deflection, and inverse Compton scattering, indicated by PDC at this point on the right. At this point, there is some angle with which the electrons or positrons will get deflected, indicated by d tilde, but that is different than the angle that we would observe d at the source, due to the fact that there is some, transverse angular co-moving distance f sub k of key to this point of interest. Now, this diagram that I've shown is very common from cosmology, in particular in weak lensing surveys. And so our goal here is to import that technology and these calculations to our setting of interest of magnetic fields rather than of gravitational lensing. And we can actually compute what these deflection angles are pretty straightforwardly. It's classically known how an electron moves in the presence of a magnetic field. And so, if you just take v cross b, but then that the velocity is directed towards us, the observer, at n hat, then you can immediately write down what this deflection angle is in terms of the magnetic field. And then you can also see that there's some critical magnetic field strength that I mentioned before, 10 to the minus 15, 10 to the minus 14 Gauss or so. That delineates a distinction between, weak deflection and full rotation. This is distinct from, say, gravitational lensing, where when you cross the critical surface mass density, you undergo some strong lensing where you get arcs and rings. You don't get that here. You just get isotropic emission. And as a result, this is what a picture for a single pair production at a single point. But, you could pair produce anywhere along this straight line, further down, further back up. And as a result, you need to integrate overall possibilities. And you have to integrate overall possibilities of where the source can lie. And when you integrate over these two distances of, where PDC occurs and where the source lies, you obtain a formula that is very, very similar to the ones using cosmology. The only main difference being is that there's the presence of this optical depth, tau gamma gamma, which indicates the probability of actually scattering at some point along this line. Now, given this, I should note once again that B here is a stochastic quantity. It varies in space. And so our goal is going to be to infer its presence by correlating distortions in the sky across multiple blazars. So there's going to be some distortion at one given blazar, and that distortion is going to be weak. This distortion, we have in fact not seen because we have not observed any blazar halos to date. So we expect it to be smaller than the background. We do not expect it to be larger than the isotropic background that we observe. But if we can effectively and robustly correlate these distortions across the sky by creating a map or so, we can, tease out this small signal, hopefully. There's a few notes about what astrophysical inputs are required into this calculation, and you can immediately see in order to calculate the optical depth, we need to know something about the intensity of the extragalactic background light, which you can just use this, Dominguez et al. Model really that fits the data, decently, but it is the standard. And then also on the left, we need to know something about the redshift distribution of the sources. Blazars come in sort of three varieties in Fermi data. They are either BL-lax, flat spectrum radio quasars, or blazar candidates that are unidentified. Unidentified ones are the most easiest to understand because, they're just ones that we don't know what they are. BL-lax and FSRQs are sort of differentiated by whether or not they have strong optical variability. So whether their optical lines vary in time very strongly. And then the total redshift distribution is in black. You should note that these redshift distributions sort of cut off at around 3 or so. There aren't many sources that are that much further. So since I've told you that this is technology imported from cosmology, it's a quick note about how cosmic shear occurs. So let's first imagine we have a source and its emission is supposed to be just some circle shown on the right-hand side by this A subfigure. It can be distorted in sort of 3 manners, and that's quantified by a Jacobian matrix A that maps you from sort of an unlensed picture to a lensed picture. And these 3 ways you can change this image are either one by magnifying it. So that's shown in this subscript, this image E. So kappa is so the convergence of your lensing field, and it can just make this image larger or smaller. In particular here, it's making it larger. If you beyond just making your image larger, you can also induce some shear, i.e. you can just make your circle more into an ellipse. And there are 2 ways to do this, indicated by gamma 1 or gamma 2. You can either make your ellipse along the y-axis, or you can sort of make an ellipse along 45 degrees relative to the y-axis. And the reason why there are 2 distinct ways to shear something is because ellipses or shear are a spin-2 quantity. You can most simply see how shear is a spin-2 quantity because of the fact that under a rotation of only 180 degrees, an ellipse returns to itself. So if I take an ellipse, rotate it by 180, I just get it's the identity operator. And if you need to rotate only by 180 instead of by 360 to get the identity operator, that tells you immediately you're speaking of a spin-2 quantity. And so this is similar to gravitons as well. The this Jacobian matrix that maps you from the unlensed to lens images is parameterized not only by these three quantities. There's also an image rotation omega. You can't really observe that. But each of these are multiplied either by the metric on the two-sphere, the Levi-Civita symbol on the two-sphere, epsilon ij, or, this shear matrix, gamma ij. And the way we do a measurement is not by just, looking at the picture and looking if it's an ellipse with our eyes, but actually computing the second moment of the intensity profile given by this Qij. So this is a quadrupolar moment tensor. You need to first measure the centroid of this image, and then choose a region around it with which to measure its intensity profile. And from this quadrupolar moment tensor, you can then extract out what the shear components are, assuming these deflections are weak. So we do not, however, just measure this on a map in the sky straightforwardly and infer what the properties are of an intergalactic magnetic field. We want to decompose this into a suitable basis. And the basis that we decompose this is a very standard one using E and B modes. E modes are a parity even aspect of these sort of shear maps, and B modes are parity odd ones. They are shown on the right-hand side pictorially. So E modes that are positive sort of make this sort of a circular pattern on the sky, while ones that are negative are radial, but you can see that under parity, they sort of return to themselves. While B modes, and I should note that the bottom right-hand version should be greater than 0, not than less than 0, actually contain some helical information about some distribution of ellipses. So namely, they either rotate clockwise on the left or counterclockwise on the right, on the bottom for those blue ellipses. And so by decomposing our maps into this basis, we can then getting information if there has been any parity information imprinted onto our sources. And this more mathematically is shown by decomposing your deflection angle D into some scalar lensing potential var phi or pseudo scalar lensing potential C. You can then recover out your lensing potentials pretty straightforwardly from the calculation of the deflection angle, as we have shown before, and then decompose it into the E and B modes using the last box indicated on this slide. And then once you do this decomposition, you can straightforwardly obtain what your angular power spectra are. So here, well, we need to first give an input for what the magnetic field power spectrum is, because this is a stochastic quantity. And as I mentioned, we are parameterizing it with three parameters. It's root mean square amplitude, which indicated here is by B sub S, for depending on which helicity it is, and n sub b, which is the index, instead of the coherence wave or coherence length. Here I'm showing the coherence wave number, which is the 2 pi inverse of it. Moreover, since we're going to be interested in a variety of different spectral indices, there is some cutoff associated with this power law indicated by the Heaviside function. So even if you have, say, a blue tilted spectrum, there is some cutoff associated. This is a phenomenological just mapping so that we can just sort of see what the effect is of these different parameters on our model. If you want to actually connect to a particular model of interest, one should do something a bit more sophisticated. So here I'm showing two examples of these parameters. So it's easy to understand what happens when you change the amplitude. The curve will go up or down. But if you have a coherence wave number shift, then actually there's a linear change in the location of the peak of this curve. And this makes sense because if you have a small scale magnetic field, then the deflection angle power will come more aptly on those small scales. So the angular wave number L, which is again maybe the 2 pi or pi inverse of the deflection angle roughly, is telling you where this peak is occurring. And while if you vary the spectral index, what it changes is sort of the slope of this initial primary rise to the peak. And it doesn't change too much things, but there are some slight differences, I would say. Yes. Now, just for examples, we're showing both a red spectrum on the right-hand plot. There's a very red spectrum of index -2 to something very blue, 3. You can have a variety of different spectral indices from the given mechanisms that I've mentioned before. You can have large scale, inflationary produced tend to go between -3, -2, -1. It really is model dependent. To something a bit more blue. If you have phase transitions, you can go even get spectra that are as steep as 5 that follow a Batchelor spectrum. You can actually infer this from just causality arguments on the magnetic field. Yes. So these are not perfect measurements, however. There are some noise in them. And so now let me spend some time talking about this noise. But before I do so, I'd like a quick question of, given that we had started late, how much time do I have left?
We still have 10 minutes.
10 minutes. Perfect. Okay, so I'll go through this a little bit quicker. And to talk about noise, we have to talk about the instrument of interest first. So, as I said, we are using the Fermi Large Area Telescope. It is a wonderful telescope that has been up in the above Earth, hundreds of kilometers, orbiting us for about 16 years now, and it seems like it's just going to keep on doing that forever until it sort of dies. There are no current plans for building a next generation gamma ray telescope, all-sky successor, in the same vein as Fermi, though there are propositions, some predecessors to propositions that are going up. And you can ask me more about them if you're interested. But Fermi itself is a pair convergent telescope. It has sort of two pieces to it that you can sort of think of. First, you have some plastic shielding. That plastic shielding prevents cosmic rays coming in to hit your detector and register as some detection. So you have this shielding. And then that just lets the GeV photons penetrate. And then in the presence of some high Z material, in particular here, tungsten, these paratons will pair convert into electrons and positrons inside the detector, and then those electrons and positrons will be tracked by silicon wafers. There's a front part of this detector that is about 14 wafers thick, and then maybe 12, and then the back part, which is 16, it's a bit thicker, and from there you can infer what the actual direction of the primary photon is. Now, given this description, the first and obvious piece of noise is the fact that we cannot determine the centroid precision of the blazar uniquely. So once again, blazars are point sources in the Fermi data, and there's some error with which we measure it. However, we will be interested in magnetic fields that give rise to, say, order degree deflections. And for the regions, the energy regime of interest, which is going to be, let's say, tens of GeV to thousands of GeV, or actually really hundreds if I want to be conservative, hundreds of GeV, you can have angular resolutions that are far sub a degree. So there are different curves here. And the reason that there are different curves is precisely because how well you can measure the resolution of your electrons and positrons that are traveling in your detector really just depends on, the angle of incidence. Not all electrons are equal, and some are just more easily reconstructed than others. If you just come in a weird angle where the detectors are not coming, then, you just can't recover and reconstruct its angle of incidence as well. And so there's these four classes, PSF0 to PSF3, PSF3 being the most accurate of these. And I should say that, while you may assume that there's the most, poorly measured things are more easier to see than well-measured things, that's not actually true. There's an even number of photons, roughly speaking, across all four of these classes. And the yellow line is just an average of the previous four. So because the angular resolution at the energy regimes of interest are not that bad, centered precision is not actually quite a big problem for our measurement. Second of all, we have the issue of pixelization. So while I've been showing previously these sort of nice, pristine images of a circle or an ellipse, in fact, we see pixels, which are squares, and squares, when put together, your Lego set does not form an ellipse particularly very well. And it is the case here, and so we do need to account for that. Here I'm showing what happens if you have an ellipse indicated in this sort of at 2 sigma shown by this blue curve. And what happens if we use our equations to recover the ellipticity. of it in the case of a pure, smooth ellipse, and in the case when you have some pixelization. And in the case of pixelization, there actually isn't too bad of a distortion of the ellipticity. And moreover, we can actually analytically compute what the effect is of pixelization is, because at the end of the day, pixelization is a two-step process. It's a convolution with a square top hat or a square window function. And then it is also a you have to sample from the center of the pixel. And both of these errors can be described mathematically, either through this convolution piece, which goes as the inverse square of the number of pixels per the size of the image. And so as long as you have many, many pixels, then you're pretty much good. And we are, in fact, in this regime. However, you do still want to account for this bias to make your measurements unbiased. Otherwise, things can go a bit wonky. And then the sampling of the center is just actually the trapezoidal rule from, integration. There's some error because we are not accurately integrating over the exact intensity. There's also the fact we have the presence of large foregrounds. These blazars do not exist in and of themselves. There is the isotropic gamma ray background, and because we have not seen any blazar halos, these backgrounds are large. And so you pay a penalty. You pay a penalty that is the intensity of the source divided by the intensity of the background in the limit where the source is much weaker than the background. And that's fine for us because even though you pay this penalty, you gain in the fact that you don't really have any other terrible sources of error. All the errors I've mentioned so far can either be corrected or they just aren't very present. It's very dissimilar from the standard cosmological analyses where you have to account for some intrinsic ellipticity of the image. Galaxies when under weak lensing actually have some ellipticity to them due to some, presence of intrinsic alignment and whatnot. But here, there's nothing of that sort really. In standard cosmology, I can make some statements about correlations between large-scale structure and gamma ray emission, but you can ask me questions if you're interested in that. But for the most part, there aren't really that many sources of error, and as a result, this penalty that you're paying because you have faint ellipses is not too terrible. There's also the fact that you have some shot noise. You do not have as many photons as you would like. And here what I'm showing on the left hand is sort of an example map of what our sample looks like from the actual Fermi data. So you take Fermi, you locate all your blazars, you want to make sure, and then you have to compute a quadrupolar moment tensor. So you have to specify some region with which you want to compute it, which depends on the magnetic field of interest. And when you compute that, you then want to exclude any blazars that are, first of all, overlapping with each other, that are blended. It's very difficult to measure an ellipse if two ellipses are on top of each other. And moreover, it's very difficult to measure an ellipse if there are other sources within it. Blazars are not the only point sources or even extended sources inside of Fermi. You have pulsar wind nebulae, you have the Fermi bubbles, LMC and SMC are present there. And so you have to get rid of all these things. And when you get rid of all your other contaminants, you have this sort of clean map of lone blazars that have nothing else in them. You have about 463. You initially had about 4,000, so there's about a reduction of about 10 in the number of blazars. But that is okay for us, because if I plot on the right the number of photons for a given region radius, I still have a good amount of photons in total, tens of thousands of photons. And so I can still get sub% precision, because it goes to the square root of the number of photons. And that's our main source of error, as I mentioned before. It's just shot noise. Shot noise is really the only thing that we have to worry about when doing this measurement. And so and because we have 400 blazars, we are also much more than the Fermi analysis, which uses about 14. You also may wonder about the fact that there's a PSF shape. So you saw the picture of the Fermi telescope. And it's a quite square of an object. So, you may be wondering if the point spread function is similarly square and not elliptical and not azimuthally symmetric. So that's actually not too much of a worry. Here's a caveat shown from the Fermi data that says that, you should only have to worry about azimuthal symmetry when you are thinking about emissions that are averaged over a few days or so. We're talking here actually 16 years of emission that is averaged. Fermi employs this rocking scheme, or at least used to, for most of its time period, that allowed it to, average over its square-like nature effectively. And so really you have azimuthal symmetry. but however, we are actively checking if this is a good assumption, because since we are using a more robust technique, new systematics are always prone to pop up when you have more precise measurements. So we are still double checking this assumption, but it is at first glance not too big of a worry, precisely because of how analyses have gone thus far. However, even if we account for all noises, you may just be distrustful of data, as you should be, and you need to have a set of null tests that tells you whether or not you can trust the data. And the null tests that we are going to be employing are twofold in nature. One, we can just look at blank patches.
We have 2 minutes left.
Cool. Yep, I'm pretty much done. So yeah, we have two null tests. You can either look at blank patches of the sky, or you can sort of just scramble your data by mixing your EMB modes at random points. And these two things, you should not, after doing these two things, you should not see correlations. They should completely destruct it. On the right-hand side, if you saw a signal, you know you've done something wrong in your pipeline. On the left hand, if you saw a signal, it may actually indicate you have some correlation that is not just located at Blazars, and in fact that large-scale structure has some correlation with GeV emission, which is interesting, but not necessarily the point. So here is sort of the money plot that I'm showing, where it shows the sensitivity of Fermi to intergalactic magnetic fields. And as advertised, you're looking between, let's say, 10 to the minus 16 to 10 to the minus 13 Gauss or so, depending on which energy photons you're looking at. We look at a variety of different spectral indices, and it doesn't change the contours too much. However, it is necessary to be precise, as previous analyses have not been as precise as we have. Yes. And as I said before, the blue box is precisely the region of where those contours lie. So I'll make some final comments on other Blazar techniques and how we relate to them. So one, Fermi does a stacking analysis. They only use 14 Blazars. We're using 400. So it's immediately obvious that we are going to have some more sensitivity. Moreover, their analysis at the end of the day is sort of a magnification analysis. They're looking for magnification of the source, which is very dependent on how bright the background is. And since the background is pretty bright, it's not necessarily the optimal thing. Here, we're looking for changes in shape of the Blazar halos, and since it doesn't have as much noise, we can actually achieve much more sensitivity than just looking for stacking. The other two methods are more follow these searches. They look for shapes. However, they either look for shapes due to some higher point function that actually seems to be not robust in the case of the Fermi handedness, or they search for bow ties, in which case they're looking for structure at a single blazar. So they look at the multiple moments of that thing. They don't just look specifically for the quadrupole moment, but all moments, but of a single blazar. And that's not as constraining if you employ all blazars together correlating across the sky. I'll leave my conclusions up, and I'll take any questions.
Thanks for the nice talk. Any question from the audience? Please unmute yourself and ask. Okay, I have one thing to ask, which I actually didn't understand. So you made a comment regarding axion and baryogenesis with respect to the magnetic fields. Could you explain it, because I couldn't. I couldn't
Sure.
understand.
So if you have the presence of an axions, you have an phi-FF dual coupling. This coupling, if you have a slowly varying field, pseudoscalar phi, will induce a tachyonic instability in your field. In particular, if you're coupled to the electroweak field, that tachyonic instability will lead to the presence of creation of one helicity of photons over another. And if the creation generates a magnetic field, which in some cases it does, the field that is generated itself will have some helicity to it, since you're only producing one type of photon. So you'll produce a parity odd magnetic field. That's the statement with baryogenesis.
But so I understand that this is a CP violating coupling, right? But does this also translate into baryogenesis? Because this is just a creation of helical magnetic fields, right?
Yes, yeah. So the way that you do it is because so you remember or recall that if you take there's an anomaly, and that anomaly is leads to a difference of left and right-handed leptons. So d mu j mu 5 is equal to a difference of it's a time derivative of the difference of left and right-handed leptons. let's say. And so what you are doing in the presence of a magnetic field, therefore, is a generation of a difference of leptons. So you each lead to leptogenesis, and then leptogenesis turns into baryogenesis. It's through the
But that is coming from a different term, right? This is not coming from the phi AF dual term.
No, it
So
is.
on
It's the
top of
anomaly.
but this is, so you want to couple it to some leptonic currents, right?
You have phi FF dual,
So
and it will source there is a term that looks like 1 over F FF dual that sources difference in lepton number.
okay, so you don't need to introduce another term which looks like del mu phi J mu.
Del
So
mu.
the moment,
I mean,
and
that's
J
a
mu
total
stands for
derivative.
the current. Yeah. So you don't need to introduce this term. So you're saying that the moment I have the phi FF dual, that
Yes.
will ensure that this transfers the helicity into also the leptonic current.
Yep.
Oh, okay. And this is at the second order level, or this happens at the first order?
This is I mean, it's first order in the field of the
Okay.
axion. Yeah.
Okay. Okay, thanks.
No problem.
Okay, thanks for the nice talk. If there is no other question from the audience, let's thank the speaker. And yeah, please.
You hear me? I've got a question.
Yeah.
Yep.
Yeah.
Thanks. So you had this list of possible explanations for why we don't see the blazars at the moment, these photons.
Yeah, the secondary
So,
emission of GeV
yeah.
photons. Yes.
Yeah, exactly. This secondary emission. So, I mean, and I guess here you've done this study, which would be sensitive to this blue box.
Yes.
So it's kind of tentative at the moment, but one possible explanation is these intergalactic magnetic fields.
Yes.
So, I mean, I'm trying to get a feeling, what do we need? How optimistic are you that what do we need to solve this puzzle? Is the secondary emission really there, or is it missing, and then we need a different explanation?
So my takeaway is as follows. If once this analysis is complete, if we detect an intergalactic magnetic field, then there is your solution. That's the first step. If we finish the analysis and we do not see the presence of an intergalactic magnetic field, then one needs to, I would say, I would start to go towards plasma instabilities personally, because BSN doesn't do it, and Blazar spectral cutoffs is just a poor choice. It's like your first guess, but it's just a poor choice. And so and plasma instabilities, the reason why they're so controversial is precisely because the way that people have simulated the instability of interest are by extrapolation to unphysical regimes. More precisely, in order to mimic the actual environments in which the instability occurs, you need to increase the number density of the plasma beams by about, let's say, trillions times higher density. Otherwise, the simulations, which are, particle and mesh or some numerical solution to your plasma system, it's just way too computationally intensive. And so people need to then develop better methods to simulate the system of interest and see whether these plasma instabilities are actually there or not. That's what you have to do to actually tell you if the plasma instabilities are a good answer. And that I would say is your next step if we do this measurement and rule out this region. Because if plasma instabilities are present, then what that means is sort of you shouldn't trust any Blazar constraint. All Blazar constraints are total crap if you have plasma instabilities.
Okay, I understand. So this is very interesting that your method actually can actually detect these intergalactic magnetic fields rather than infer their presence with some assumptions
Yes.
because you don't see anything.
Exactly.
Okay,
So
very
more
good.
precise. Yeah. So one of the things that we wanted to move away from is information about spectral shape. So, measuring the spectrum of a blazar is quite or inferring the intrinsic spectrum of a blazar is quite of a nefarious process. One must measure you see your spectrum in Fermi, you then have to fold in information from Cherenkov telescope arrays. But the thing that you see at the Cherenkov telescope arrays isn't the actual spectrum of the blazar, because you have still this optical depth. So you have an absorbed spectrum that you do that you need to deabsorb, infer the intrinsic spectrum of the blazar at these high energies, and then extrapolate it to low. You can imagine that this process is quite messy for an astrophysical system. And folding in information about energy just seems like the wrong way to go about doing things. And morphology is a much more robust system that has even more higher precision, I would say.
Okay, thank you very much.
Okay, if there is no other question from the audience, let's thank the speaker again, and let's close today's session. It was a very nice talk. Will you be able to send us the slides for
Yep.
our seminar library?
Indeed.